Yes, yes. Hi everyone. Good morning. Yes, good morning everyone. Hi. All right, all right. So, what was the last part that we have discussed? Yes, guys. What did we study in the last session? Second phase, deep learning. We have seen. Okay, okay. In in today's first half, guys, we are going to see the back propagation algorithm. Right? What do you mean by back propagation? I'll just take out for you just a minute. Feed forward means suppose these are the three input layers. Do you have three neurons? This is hidden layer and this is output. So for this there will be weight associated, right? This one weight, this one weight. So likewise it is connected to all the layers out there, right? And there will be addition of bias at each term and there will be output y, suppose. So if you just consider one layer, so this is your hidden layer, this is your input layer, this is weight, this is bias. So at this point, it will be, excuse me, yeah. At this point, it will be A1 W1 plus B, right? That will be Z. Yes or no? We have seen that. Now I'll be just having an introduction to, I'll be giving you guys an introduction to back propagation. So you have studied feed forward network. How does the model works? How does the model learns? Yeah, we have seen that, right? How does the model learn? This is Z1 equals to W1x1 plus W2x2 plus W3x3 plus this bias term. That will be your output, right? This is a representation of cumulative input. And there will be a loss function in, in classification model. In classification model, we have entropy, cross entropy, right? And in regression model, your loss function means the function which you calculate is very simple. It is your mean squared error, right? I'll be just writing down over here. So we'll first of all see that, and then we'll be going to the next part. So let me just have a look at, or let me just write down your feed forward neural network. That is something which we are going to study in today's session, right? So everybody has understood that how does the model work, right? Will in this session we are going to learn how information flows. You already know that. I know this. You already know that. We have seen or we have discussed how the information flows, and you know uh, how the information flows from input layer to output layer, right? Input layer from input layer to the output layer, and which makes us the neural network to enable enable the neural network to make a prediction. To make a prediction, right? The information flows in this direction is often called as information flows. In which direction? This forward direction is often called as feed forward. And you'll also learn how to assess performance of a neural network. How to assess performance of a neural network. That is something which we are going to learn, right? So it's very simple. Hardly it will take 10 or 15 minutes. So let's get started with this. You already know how flow of information happens between the layers. Nothing new in this. How does the information flows? How does it flow, guys? How does the information flows, guys? So it will be like this. Suppose if I just have to draw the diagram, the diagram is, matrix representation is, suppose I'll be just giving you guys, let me draw three input neurons, 1, 2, and 3. This is W1, this is W2, and this is W3. So it is going to be W1, W2, and W3. This is going to be X1, X2, and X3, right? And this is going to be function of Z1, Z1. Simple. Now, suppose if I just add another, you know, hidden layer, that will be function of Z2, right? Now, now, see, I'll just write down, let me just take this figure. Let me just take this figure. Let me remove this and let me paste it over here. right? Now Z1, Z1, I'll just write down the equation for that. You guys know that, everyone. It is W11. Now, what happens is, guys, if you have multiple hidden layer, so this particular line becomes W21, right? W21. This becomes W22, and this becomes W23, right? Weight of hidden layer, weight associated with hidden layer 1 and with input layer with hidden layer 2 and with input layer 1 is given by weight 21. So this is weight 21. This is weight 23, right? And similarly, this weights now become W11. This becomes W12 because first input layer, first hidden layer, second input, first hidden layer, third input is W13, right? So W13, W12, and W13. Sorry, W11, W12, and W13. This will be W21, W22, W23. Right? Everybody knows that. So I'll be writing down W11, X1, because this is W11, X1. This is W12, X2, and this is W13, X3. Simple. So W11 X1, W12 X2 plus W13 X3. Getting it, guys? Plus bias 1 is something. Bias 1 is something which we are going to add. And this will be W21 X1 plus W22 X2 plus W23 X3 plus B2. Right? Getting it, guys? Everyone? Now, if we have to write down in the matrix form, it will be Z1, Z2, right? And there will be a, matrix of W11, W12, W13. This is W21, W22, W23, and there will be a X1, X2, X3. Suppose we have three inputs. Anyway, here we have three inputs. So W3. And, so this is another matrix. This is another matrix. And there will be bias matrix, right? So that will be plus. That will be plus bias. That will be B1 and B2. That becomes your matrix multiplication, matrix representation. Simple, nothing difficult in that, right? So it can be written down like Z1 is equals to W11 X1 plus W12 X2 plus W13 X3 plus B1 W21 X1 plus W22 X2 plus W23 X3 plus B2. Right? Simple. Getting it, guys? Everyone understanding it? Yes, guys? Now what happens is in layer 1, the representation is how it is. See, suppose if you know this is your layer 1, if this is your layer 2, this is function of z1 of 1, and this is 1, this is 1, this is function of z1 with respect to 2 because second layer, and function of z2 with respect to 2. That is your node 1. That is your node 2, right? And this becomes your formula like this. So it will be W112, W212, right? As simple as this. Getting it, guys? Understanding it, guys? So that's your notation. Like if you are writing down W112, this one represents position of neuron in the current layer. Position of a neuron in the current layer. And this one represents position of input from the previous layer. Position of input from the previous layer. Position of the input from the previous layer. Yes or no? And this two represents layer in which we are talking about. Right? That is how the representation is. I think everyone has got that. Let me just take it over here. And I'll be giving you guys some diagram. Just give me a minute. Let me give some diagram for you. So that is how the representation, the notation is, right? So that is matrix representation, and that is your another notation. Just give me a minute, guys. Yeah, so you guys want that diagram of flow of information between the layers. Yes. Yes, this one. Yeah. This is first. So instead of me writing this down, just take this for you. This is your first diagram. And the second is this notation of neurons wet in a particular layer. Goes like this. Right? And I'll be sharing my screen now. This is very important. If you are explaining someone this process to the interviewer, you should be able to understand the notation, right? Most of the guys don't know this. So if you are, good in deep learning itself, their chances will increase. Till machine learning, everyone is perfect. Everyone is good. But trying to understand deep learning is a challenge, is a big task in itself. So if you just know deep learning, then you stand out differently from the participants that have applied for for the particular job, right? Now there will be In addition to this, just a input, there will be an activation function, right? So this is your matrix representation. This is how the diagram goes. There will be some layers like this, then like this. The next step will be an activation functions to the z1 vector obtained from the h1, this one. So after calculation of this matrix, next step is to apply the activation function, this one. So this is your two equation. These are the two equations that we have, and that will be passed through the activation function. So after um, hidden layer, there will be an activation function. So w1 x1 of b and activation function. So next step is to apply activation function to the z1 vector to obtain the output h1. As mentioned in the video, activation function is applied to each element of the vector. Thus, final output h1 of layer 1 is this. I'll be giving this in the form of presentation, guys. Don't worry. I'll be sharing this in the form of PPT. So to summarize the steps involved in the computing the output of ith neuron in layer L is as follows. You have to multiply each row of weight matrix with the output from the previous layer to obtain the weighted sum of the inputs from the previous layer, right? And you convert the weighted sum into cumulative input by adding a bias vector. Bias vector is added, and then you apply the activation function sigma x, depending upon the choice of activation function that you have, to the cumulative input to obtain the output vector h. Simple, right? So that becomes your feed forward network. Now let's go to the next segment, forward passing. Then what happens is, let's take this example. Let us take this example. To reiterate the problem statement, uh, we have to predict the price of a house given the size of the house and the rooms, number of rooms available. Let's take this problem statement and let us try to work on this, right? So what I'm going to do is the house. Then okay. Okay. So this is the problem statement. Let me draw that data. Let me just plot that data. This is standard number of rooms. This is standard house size. And this is price in dollars. Right? So number of rooms are 3, 5, 3, 3, 4, 2. House size is 1340, 3650, 1930, 2000, 1940, and 880. And price in dollars, C13000, 2384, 000, 342000, $420, $420,000, 550,000, and 490,000. Right? That becomes your, data set. Right? Now in this case, we have to, scale the data. So we'll be scaling this data. Scale the data. Anyway, this is something which we are going to do practically as well. So we are going to scale the data because if we see all the data are not in a single range. So I'll be just taking this data, kind of, scaled it by using normalization or min max scaler. So it becomes something like this. Minus 0.32, 1.61, minus 0.32, minus 0.32, 0.65, minus 1.29, right? House prices becomes minus 0.66, 1.80, minus 0.03, minus 0.03, minus 0.02, minus 1.15, and your price becomes minus 0.54, 2.03, minus 0.51, minus 0.41, minus 0.25, minus 0.32, right? And as you saw, we'll build a neural network that will predict the price of a house. So given that two input attributes, we will build a neural network that will predict the price of a house. Simple. So given that we have two input attributes, that is number of rooms, and house size. Let's start with the structure of the neural network that we'll consider for this case. So we have an input layer with a two input node as x1 and x2, one hidden layer with two nodes and a sigmoid activation function. Sigmoid activation function. You already have imagined now how the neural network will be with two nodes. And finally, output layer with a, because this is a regression problem, so it will be linear activation function for, you know, output, because it's a regression problem. Getting it? Excuse me. So let me just take the layer. This is our, just go through this, guys. Just give me a minute. Right? So this is your layer. This is your network. Right? Now to understand how the data moves forward in the network, to enable neural network to make predictions, we'll initialize the weights and biases with the random value. Weights and biases are assigned to this. We recommend that you keep a pen and paper, uh, you know, handy for practicing the computations that will perform further. The intention is that as this network gets trained, the weights and biases will be updated as per the data, such that the predicted output will eventually be the same or at least similar to the actual output. Right? So let us start assigning the weights and biases. So my layer 1, for my layer 1, weights and biases are this one. Right? And you already know superscript is nothing but, so this is W11. A superscript denotes the layer to which it belongs to. So this one belongs to the layer. This two represents the layer to which it belongs to. Getting it, guys? Now remember, the superscript denotes the layer to which it belongs to. Superscript denotes the layer to which it belongs to, and the subscript denotes the node in that particular layer. So to showcase the step-by-step computation of the output, to showcase the step-by-step computation of the output. Let's take the first example as the input vector, right? Yeah. So this is my x1 and x2. This is minus 0.32, this is minus 0.66, right? Now, let's compute the output from the first node in layer 1. Let's compute the output from the first node in the layer 1, right? So let us assign the values to this. This becomes your value, right? Now we are only focusing on layer number 1, guys. Only focusing on layer number 1. We are going to focus on layer number 1. So the calculation becomes W11, this is W11 into X1 minus 0.32, W12 into X2, right? Plus this bias, right? So it will be 0.2 into minus 0.32, 0.2 into minus 0.32, minus 0.66 plus 0.15 plus 0.1. And that will become your output. And then you are going to apply a sigmoid activation function, on that input to get the output. So you have computed this, right? You are getting it as, 0.063, applying sigmoid activation functions to obtain the output from the first node. H1 equals to this, right? And then, layer 2 comes into the picture. So node 2 comes into the picture. And for that, calculation will also become simple for us. This is your computation and this is your output, right? So let's not waste our time in, writing down the things because we already have this. So again, this becomes node 2 becomes W21 into X1. This W21 into X1 because, this W21 comes from X1, right? This one. Then W22 into X2. Simple. Plus this bias 0.25. It will be minus 0.306. And you're going to apply a activation function, sigmoid activation function on this thing 0.306. So get the output. So first hidden layer giving me the output as this, second hidden layer giving me output as 0.424. Now what happens? See, next step. Next we'll go to the layer number 2. Next we are going to the layer number 2. Layer number 2. Right? You can always put this, in a matrix form like this. That is your matrix form, matrix calculation for a reference. And then, third layer, layer number 1, layer number 2, node number 1 comes into the picture. So there will be 0.3 into this 0.1, 0.2 into this 0.25, something like that will happen. And final output you are going to get. So let's take W11 H1 plus W12 H2 plus B2 B1 is equals to this. And since this is a regression problem, we have considered that activation function is a linear activation function in the output. So the input is sent to the output without any modification. Hence the output is the same as the cumulative output, that is 0.63, right? So this 0.63 is a prediction of the neural network, makes that in a first forward pass, right? This is just a first forward pass that we have, right? So in this network, this is first forward pass, output is 0.63. Simple. Now in your real, this is your matrix multiplication method. You can just have a look at this. And as I told, in real life scenario, you guys will be having multiple passes, right? Forward pass, then backward propagation, forward, then backward. Multiple epochs will be there. One forward, one backward is an epoch. Why there is need of backward propagation? Because the output that you get is not, close to the real output or actual output, right? Your model has predicted 0.63, but your actual output is something different, right? So, since the performing forward pass through the neural network using the input as 0.32 and 0.66 gives us the output as 0.63. The prediction is very different from the actual value of minus 0.54. Actually, it was minus 0.54, guys. Can you just imagine? Actually, actual value was minus 0.54, but model has predicted what? Predicted value is, 0.63. 0.63. Getting it? So actually is minus 0.54. Getting predicted is 0.63. So this was a demonstration of how information flows in the forward neural network from the input to the output. And that is the forward pass to make a prediction. One forward pass. Easy. Now, in the next segment, we'll introduce a concise algorithm that can be used for any feed forward neural network. That is feed forward algorithm, right? So this is nothing but just a comprehension of what we have studied. Let me just take out that. We have to write down the pseudo code for the forward propagation or forward pass. And that is nothing but the pseudo code of a forward feed forward pass is given below. We initialize the variable h0 as the input h0 is equals to xi. We loop through each of the layers, computing the corresponding output for each layer, that is h1 for 1, 1, 2, 3, 4, L. h1 is equals to sigmoid of w1 h of L minus 1 plus b1. You already know that. And we compute the prediction by applying the activation function to the output from the previous layer. That is, we apply the function of hl as shown in the below, as shown like this, right? So there are some important things to notice here. In both regression and classification problems, the same algorithm is used till the last step. Yes or no? The algorithm is same. But in the final step, classification problem P defines the probability vector, which gives the probability of the data point belonging to a particular class among different possible classes or categories. So classification, there will be classes in the output, and regression, P represents the predicted output obtained, which will be normally referred to HL, because in regression problem statement, we use linear activation function. Linear activation function. Getting it, guys? In regression problem, we are getting linear activation function. In, regression problem, it is linear. In classification, because that is as it is a classes, so there will be softmax. There will be softmax activation function. Getting it, guys? Understanding it, guys, now? Very simple, very simple. So I think these are the mathematics. Don't need to, remember this more normalizing vector and something like that. For regression problem, we can skip the third and fourth step, that is computing the probability of normalizing the predicted output vector. Because we don't deal with the probability, right? In your regression. So the primary goal in machine learning is to get predicted output to be the same or close as to the ground truth output as possible. We have seen the forward algorithm and learn how to compute each element in an NN. Now we want to train the neural network to get the predicted output as close as possible to the actual output. In order to do this, in the next segment, we'll discuss the loss function, which quantifies the difference between the predicted and the actual output. Now we have a loss function. And that is nothing but same like you guys have seen, mean squared error, residual sum of squares, right? It is totally same. It is going to be same only. So I'll be just writing down the loss function. And let's put this as heading. Let us put this as heading. Right now, uh, in your loss function is nothing but, guys, cost function that maps an event or values of one or more variables onto real number, and that is nothing but this difference between actual values and predicted values, right? The same example we are going to take, suppose, and we'll see how adjustment is done on the subsequent section. We are going to compute the loss. So what is your loss function? Very easy definition: difference between actual value and minus predicted value. Simple. So if you just do this, in case of regression problem, the most commonly used loss function is mean squared error. In the case of classification, the most commonly used loss function is cross entropy log loss function. Getting it, guys? So that is your idea over here, right? Now, these are the examples that they have taken. Like this is your, data. This is your network. Loss function they have calculated as 1 minus half of actual minus predicted square. So actual it was minus 0.54, predicted is minus 0.62, loss is 0.6844. Now as given above, mean square error is a mean square error of all the samples in the given data. This gives us the quantified method of measuring how well a neural network is predicting the output, right? So let me just take this for you, so that you can get an idea about the loss function in regression problem. In classification, it becomes, for classification problem, it is cross entropy log loss, or cross entropy or log loss. We'll see that. As this is a regression problem, so, for each and every layer out there, prediction, actual, prediction, actual, prediction, actual. So it will calculate the, you know, uh, cross entropy. We have, do you remember we have studied entropy concept? Where, in which machine learning algorithm we have discussed this entropy concept, guys? Do you remember this? In which machine learning algorithm we have discussed entropy concept? Yes, guys. In which machine learning algorithm we have discussed the entropy concept? Nobody remembers this? Strange. In which machine learning algorithm we have discussed the entropy concept, guys? Nobody remembers. Decision tree, correct. So something like that we use over here also. So for classification, there will be entropy concept like this. Getting it, guys? So entropy is nothing but like this only. Like this is a predicted output probability. This is actual probability, predicted, actual, predicted. So it is summation of negative y into log of probability of I. This one, like summation of y into log of probability. This is your output. Getting it, guys? Understanding it, guys? Yeah, if it is clear, let's go to the next part. Let me check what is next. Huh. So like loss function is something. Huh. There is a gradient descent algorithm. Do you remember that gradient descent? What is that? You know, on your y-axis, we have loss function. On y-axis, you have loss function. And on x-axis, you have weights, right? So the graph is like this. Initially, you assign any weight, random weight. Suppose it is over here, random weight. And you observe that loss function is quite high. There is chance of, there is chance of minimum cost function, minimum loss function. And our whole idea is to achieve this minimum point, the point where we have minimum loss function. Understanding it? Minimum loss function. So we have to achieve this position where we have very less minimum cost function. So we are going to reduce the weight, or modify the weight. So weights are updated like this. And then we achieve this position, right? The step that we take to achieve this is, the step that we take to achieve this is known as learning step or learning rate. So might happen that, learning rate can be high. So only these steps are possible. Only these steps are possible. Only these steps are possible. So you'll not achieve this minimum loss function. But if the learning step is very less, very less, it should be very less actually. It should be less, so that there will be reduction in the loss function. You'll observe that easily. It will be here, here, and that will be there. And then you observe that you again go here. You observe that there is increase in the cost function or loss function. So I can say that this is my global minima. And this is my particular point where the loss function is minimum. So that is what we have to achieve. So we have to achieve a combination of weights and bias. Combination of weights and bias. If you use that, there will be minimum, or very less cost function. Right? Understanding it, guys? So that's how they have explained this, what is learning in the neural network. Like we have to minimize the cost function by using a gradient descent approach. The task of training neural network is similar to that of other ML models such as linear regression or logic regression. We have discussed that. The predicted output from the last layer minus the actual output is a cost function. And as we have to tune the parameters of W and B such that the total cost is minimized. The total loss function for a regression model can be given like this. It can be given like this. Right. And to start training a neural network, we randomly initialize the weights at the outset. An important point to note is that if the data is large, which is often the case, and the loss calculation itself can get pretty messy. For example, if you have millions of data points, they will be fed to the network in batches, and output will be calculated using feed forward, and the loss per cost will be millions of records. So there will be calculation of loss for first data point, second, third, fourth, fifth, sixth. So for millions of data point, it will be very hectic, right? And this is not this is not the method that we should follow for a large data set. And in real world scenario, the reason why we use deep learning is nothing but we have millions of billions of parameters in the data, right? Real world scenario. That's why we have discovered this deep learning approach in order to solve the complex task very easily, right? So the total loss function is W's and B's. And once the total loss is computed, the weights and biases are updated in the direction of decreasing loss. In other words, L is minimized with respect to the W's and B's, right? One important point to note here is that we minimize the average of the total loss, not the total loss. We minimize the average of the total loss. And you'll get to see this shortly. Minimizing the average loss implies that the actual loss is getting minimized, right? So we don't minimize the actual loss or total loss. We minimize the average loss. So this can be done using the any optimization routine such as gradient descent. The parameter being optimized is iterated in the direction of reducing the cost according to the following rule. W new is equals to W old minus alpha of WL by the delta W. The same can be written for biases. You have to note that weights and biases are often collectively represented by one matrix called W. And going forward, W will by default refer to the matrix of all weights and biases, right? So the main challenge is that W is a huge matrix, and thus the total loss L, total loss as a function of W is a complex function. Uh, that is something which we have to deal with, right? So this is your, excuse me, this is your gradient descent approach, guys. This is total weight is equals to old weight minus learning rate times dl by dw. And what is dl by dw? It's a, you know, gradient. Gradient means we are reducing that gradient. So that's why it is called as gradient descent approach. And this is a real approach that we should follow, not the one in which we calculate loss associated with, each and every single parameter out there. That is not something which we should do, right? So that is your gradient descent approach. Let me know if it is clear, guys. Now, are you guys understanding this? Very simple concept, nothing special. Like, as we have already, become expert in machine learning. So the optimization of cost function is something which we are not going to study because it's the same approach. Getting it, everyone? Can I get a response from everyone now? Yes or no, guys? Now we'll do some practical implementation. Let's have a break till 10:15. Meanwhile, if you have any questions, just write down in the chat, guys. I want everyone should ask questions, guys. So we use gradient descent to minimize the loss function. Correct. Murli. In everything like machine learning, you know, your deep learning, RNN, CNN, we use this approach, gradient descent. I'll be just taking this figure. Let me copy this. Let me paste it over here. All right, guys. All right. So now we will be going to the next part, that is back propagation. Having understood what is, forward propagation, let us now try to understand what is back propagation in neural network. So this is your back propagation, right? Now, introduction to back propagation. In this session, you learn about the process of training neural networks, which is called back propagation, right? Here are the following topics that we are going to cover. First is gradient descent in neural network. Then we have back propagation algorithm. Then we'll see introduction to TensorFlow, because in the last session we have not seen that. We'll see this, and we'll implement, a neural network using TensorFlow. Even though it's not recommended nowadays, we don't use TensorFlow, we use Keras, because in TensorFlow you have to, give weights, assign weights, biases. In Keras you don't need to do that. In the last session we have discussed that, right? So what is back propagation, guys? So it is nothing but after doing gradient descent, we have to modify the weights, update the weights, right? So what happens is, suppose actual value was minus 0.54, predicted value is 0.63, right? And the hidden layer, uh, we'll be using back propagation to compute this gradient. Which gradient? This one. Just a minute, I'll just show you this. This one. Yeah. So the, you know, to find the optimal combination of weights and biases, we minimize the total loss with a fixed set of hyperparameters. The optimization is achieved using a familiar gradient descent algorithm. And now we'll learn about the backpropagation. Which is nothing but gradient descent algorithm is this, right? Where K and J are the indices of the weights and weight matrices, and L is the index of the layer. So this is your layer, suppose, right? Now what we'll do is, given the neural network diagram, the output layer will be following weights and bias term will be updated. Which weights and bias? W11, W12, W22, W21. These are the weights and bias that you need to update. right? So W11 square is equals to W11 square minus NWL divided by W1. This one, W12 square plus B1 square is this, right? Now, for the hidden layer, the following weights and biases will be updated. So for hidden layer, we have these weights and biases that will be updated. And to compute this gradient, we use an algorithm called as back propagation, right? And as you can saw in the formulas, there exist partial derivatives of the total loss with respect to weights and biases in these equations given above. To compute this, we use the chain rule. And you can observe the dependencies of different layers in the gradient computation. Now, let's simplify the neural network given above and represent it in a condensed format like this. So we have W1 B1, W2 B2, and this one, right? Now in this case, the loss function is a function of W1 B1, W2, and B2. The loss function and the activation function and the cumulative input are shown in the following expression like this. Loss function is this. Cumulative output is this. Output is in tan h. Activation function is this. Now, what we'll be doing is we'll be computing the gradient of loss function with respect to one of the weights to understand how the back propagation works. Suppose we want to find delta partial derivatives of loss function with respect to weights 2. This one, right? Now we use a chain rule to find that, guys. So WL with respect to W2, W delta L with respect to delta W2 is equals to, it becomes delta L divided by hidden state, uh, hidden layer. Delta H2 with respect to output of the second layer into delta Z2 with respect to weights, right? So it will be Z2 Z2 will cancel, H2 H2 will cancel. It will be delta L with respect to delta W2. So it's a chain rule we have to use because we cannot directly find delta L with respect to delta L W2, right? Because loss function and weights are not directly associated, right? But it can be associated like this. Now, based on the definition of loss function, is a direct function of H2, H2 is a direct function of Z2, and Z2 is a direct function of W2. That's how we calculate the loss function or gradient by using a chain rule like this, right? So let me just take it over here. Let me just put it over here so that you can get an idea, right? So that's how it is calculated, guys. And this is for first term, second term, uh, taking the derivatives of loss function L with respect to H2, delta L H2 is equals to delta H2 into 1 by 2 into y minus H2 square is equals to minus y minus H2. Second term is this, applying the tan h activation functions on the cumulative input Z2, we get H2. H2 is equals to tan of Z of Z2, right? And taking the derivative of H2 with respect to Z2, delta H2 with respect to Z2 is equals to 1 minus tan H square Z2 is equals to 1 minus H2 square, and this one, right? Now, we have a third term that is cumulative input Z2 is equals to W2 into H1 plus B2. And we are going to take the derivative of Z2 with respect to W2, that is delta Z2 divided by delta W2 is H1. This is mathematical calculation, like you don't need to worry about this. And there will be finally, this equation will be, we are going to get to, find the loss function with respect to W2. Now we have completed the computation of gradient of the loss function L with respect to W2 for back propagation. We can simply compute the gradient of loss function with respect to all the weights and biases present in the network like this, right? So let me just take out this and give it to you. Right. This becomes your, formula. No, nothing to remember. I mean, you don't need to worry about this. We actually know. We also don't do this manually by using TensorFlow library. We have Keras, high-end Keras API, and we make use of that so that we don't need to assign weights and biases as well, right? We're not going to assign that. So this is for all the layers out there, and it becomes a little complicated. We'll not be actually having a look at that. Then there's a numerical examples for backpropagation. We can take the same weights like this, biases, figure becomes like this. We have calculated earlier, it is coming 0.63, actually is minus 0.54. Now let's revise the notations like this. These are the notations. We'll now focus on updating weights and biases in the network. And we strongly recommend that you perform the calculation yourself along. I mean, you can also do this. So this is your output for the hidden layer, right? And then there will be a gradient descent like this. Gradient descent, gradient descent. It will be like this. The weights and biases will be updated. New weight becomes 0.1867. And then new updated weight 12 becomes 0.1008. Similarly, for the bias term also we can do that. And biases also will update that. So we have updated weights, values of weights and biases of the output layer from single iteration like this. And then again, the forward propagation will happen by considering these weights. There will be some output. Obviously, it will be enhanced, it will be improved, which will be somewhat closer to 0.54, not closer to that, but somewhere earlier it was 0.63. Let's say it becomes 0.15, but still it's not close. Then again, we can go back, update weights and bias. Like that, it will happen. There will be multiple epochs, 500 epochs, 1000 epochs, 10,000 epochs in the output. So one forward, one backward. Likewise, there will be 10,000 epoch. Can you just imagine? So that's how the model learns and, reduce the error that it is getting. Now, can you see? Again, we are updating weights. Likewise, it is continuation of the process. This one, this one, this one. Getting it? Now, we'll not go actually in the mathematical part. See, now it is changed to 0.2623. We'll not be going to the mathematical part. And also, it's not required as well, but you should know the procedure, how it happens. So that's why we are discussing this. So earlier it was 0.63, now it is 0.2623. Getting it? And now, the steps are like that. We took the following steps when passing an input through the network. These are the steps that we have. Forward propagation, backward propagation. And we'll repeat this process until the model gets acceptable predictions. Now, same thing, like you can do the same thing by using TensorFlow. It's very, very, very complicated. Like you have to define the gradient. You have to define, the weights and updates, weights and bytes. You have to do the calculation. Getting it, guys? So it's kind of, it's very complicated and you don't need to worry about that because nowadays we don't use that. Yeah. But I'll just give you guys an idea about that, a quick overview of how to build the neural network using TensorFlow. And then we'll actually going to build, work on the Keras library, Keras. So TensorFlow fundamental is something which you should know in order to understand and get started with the TensorFlow library. Let's discuss this. Okay. I think this is not something which I have. Not one. This. Just a minute. Right. Not this. Actually, this one. TensorFlow fundamentals. This. Okay. Okay. I have not uploaded it. Is it? Correct. This one. Yes. Getting it, guys? Now we are going to cover these two topics. We are going to cover these two topics. And what are those two topics? Hmm. Yeah. So how to create tensors? Two ways of declaring tensors: mathematical operations and linear algebra. Right. Now, following topics are covered in the optional sessions titled as Advanced Operation with TensorFlow. Like how do you reshape and broadcasting and automatic differentiation? That is something which you can explore by yourself. But I'll just give you guys an idea about the TensorFlow library. So if you're working with the Jupyter notebook, guys, you need to install TensorFlow by using pip install TensorFlow. In Colab, as TensorFlow is a library of Google only, Google has developed that. So this Google Colab provides you know, provides a provision in which it is automatically installed. You don't need to worry about that. Simple. Now, now, uh, yeah. So we are importing TensorFlow as this. We are importing um, NumPy as NP, tensors with different ranks. Vector in TensorFlow is this vector underscore tf is equals to tf dot constant. This is a constant. Vector underscore np is equals to np dot array. This print shapes vector dot tf dot shape np dot shape. So this is how you create a constant. Tf dot constant is a uh, function or is a method that we have in TensorFlow library to create a tensors. Now, what is tensors, guys? Tensor are nothing but similar to your NP array. Do you remember NP array? Here we have tensor. So TensorFlow library deals with tensors. NumPy deals with array. Simple. It's an analogous. It deals with array. NumPy deals with array. Getting it, guys? So TensorFlow deals with tensors. This deals with NumPy deals with array. So this is how you create a tensor. Write down this, guys. Write down this. First of all, you have to do this simultaneously with me. Import TensorFlow as TF, import NumPy as NP, and you know, import this. Write down this. Do this thing. I'll give you 5 minutes of time, everyone. Do this, guys. Write down this, guys, and let me know if it is done. Done, guys? Perfect. So now what you have to do is you have to print the shapes of this. So we have defined an array, we have defined a constant in TensorFlow, we are defining a shape. So vector underscore tf dot shape, vector underscore numpy array dot shape. So it is 5 cross 5 comma 1. We have 5 rows, sorry, 5 column and 1 rows, right? We have 5 rows, sorry, 5 column and 1 row. Simple. Getting it? So write on this, and then we'll define a multi-dimensional array, multi-dimensional constant. So write down this as well and print the shape. Then we'll define 3-dimensional. So likewise you have to do, I think it's done here. You can write down this. You can write down this point. I'll give you 5 minutes of time. Write down this. This is your introduction to TensorFlow, right? We have seen Python introduction, just like that. This is our introduction to, you know, TensorFlow library, similar to the NumPy library and Pandas library that we have discussed. Is it done, guys? Done, guys? Is it done? All right. See, so the shape is, for this it is 5 by 1. For this is, it is 3 by 2, 3 by 2, because we have three elements, 1, 2, 3, and two dimensions. And this is three-dimensional tensor wherein we are, giving data type as float. This is float data type. So we have five elements. I mean, five would be there. Into five means this will be repeated five times. So five dimension, three elements, 1, 2, 3. In that you have two elements. So 5 by 3 by 2, 5 by 3 by 2. Simple. Then here, if you see, data type is float, because for this we are assigning 0 point this, 0 point this, 1 point this, 2 point this. So it's a float value. Now you have a question. Question is declare a tensor of shape 2 by 2 by 2 by 2 with random numbers from normal distribution whose mean is 1 and the standard deviation is also 1. So you have to define a tensor of shape 2 cross 2 cross 2 cross 2, 4 times 2, with random numbers from normal distribution whose mean is 1 and the standard deviation is also 1. So approach number 1 is you have to initialize the n-dimensional array in NumPy, then use that to initialize the tensor. Array is equals to np.random.random n 2 cross 2 cross 2 cross 2. It returns the random numbers from standard normal distribution. Mean is equals to 0, standard deviation is equals to 1. Then you'll print array.shape and then you'll print ARR, right? So ARR is equals to ARR plus 1. Adding 1 makes the random number from normal distribution which has mean is equals to 1. Not needed, guys. Don't try. I mean, don't worry about this. So np.random.random number 2 cross 2 cross 2, right? So we have created this. Approach 2 is TensorFlow you can use. So TensorFlow.random.normal. This. And mean is 1. Standard deviation is 1. Name is my underscore tensor. So you have my underscore tensor in which you have created a random number whose mean is 1, standard deviation is 1. Then there are two ways of declaring tensor. You can use constant or you can use variable. Variable values can vary. Constant value is constant. Now declaring tensor with specific data types. You can give data types as integer 32, data type as float 32, data type as boolean, right? Then, you know, uh, what we can do is, yeah. Now integer 32 dot tensor dot numpy. So it's something which we use to create an array. Then common mathematical operation on tensor is multiplication, right? Range function you can add. Then you can add x plus y, x into y, y by x, like that, right? Then you can write on tf dot add, tf dot multiply, tf dot divide, right? Note that element-wise operation does not work if tensor have different shapes or cannot be broadcasted, right? So transpose of vector is this, tf dot variable, tf dot transpose. Linear algebra on tensors is this. Like you can use linear algebra mathematical multiplication, multiplying these two tensors, right? Inverse you can take. Then eigenvalues you can find. Suppose this is your linear equation. So you see, you have to define this. Can you say this tf dot variable 1, 1, 1, 2, 3, 2, 3 minus 1, 0. You are defining this and then you are doing mathematical operation on that. And last but not the least, there will be a, you know, what we can say, the gradient descent type, the differentiation should be there. See, differentiation, just like your gradient descent. W respect to W loss with respect to W2 new is equals to W loss W2 old minus alpha times likewise something was that, right? So you're finding the gradient differentiation, gradient you're finding, no? So that is something which we can also do mathematically by just defining. So in earlier days when you don't have, when they don't had keras, they were doing like this. They used to do like this, right? Then gradient for model training. So number of feature you're selecting. Weight is this. Bias is this. Number of samples. X and Y. Gradient descent. And then you're getting the output. So how do you disable gradient computation? Like they used to do like this, but now it's very simple. You don't need to worry about that. Nobody does this. We are on the safer side, right? Chalo. I think we can, go to the next part. I'll be just sharing the dataset and we'll be building the um, model using Keras now. I think in the last session we have discussed this. Yes or no? We have built the model, right? The last session. That's the reason I'm not doing it live. Correct. Where we have done this the last session. Now, do you remember I have given you guys this task where we were interested to, uh, we have taken a real data set, this one. Then we have done the scaling standardization. Here also, this is your data set. We are doing scaling. Can you see this? Scaling. Then we are getting this. We are, dividing your data into X and Y. Dividing your data into X and Y. Then you are creating model using Keras. Model using Keras. Create model using Keras. And, from TensorFlow, we are importing Keras. Then you are defining a shape. Sequential model will be there. Adding keras.layer.input. Shape is x.shape -1. Keras.layers.dense 2, comma actation sigmoid. Then there will be linear actation function, and then you're doing model.summary, right? Now you're defining random init parameters, and you're defining a weight, bias, weight, bias, right? And forward propagation, you're creating a function. Z1 will be, what is that? W1, X1 plus bias. So TF dot mathematical multiplication of what? X and W1 plus bias. H1 is equals to TF dot H1 is equals to sigmoid of this one, no? Sigmoid of Z1. So H1 is equals to TF dot math dot sigmoid function. You're applying activation function to that Z1, right? Simple. Now I think you will get it because since we have studied this basic TensorFlow operations, random, uniform, mathematical multiplication, math. So you'll understand it now. Z2 is equals to TF dot mathematical multiplication. Z2 is equals to H1 into W2. Sorry. Hmm. Correct. H1 into W2 plus bias. So mathematical TF dot mathematical multiplication of H1 into W2 plus bias. H2 is equals to Z2. You are going to return Z H2. And you are going to compile this model by using loss is equals to, as it is regression problem, we are using mean squared error. And keras.optimizer is equals to stochastic gradient descent. This is gradient descent, guys. Optimizer means if we have to, uh, do the gradient descent, which method you are going to use? You are going to use stochastic. We'll see this thing in the next session. What are the different types of gradient descent? I'll discuss that one by one. So can you see this now? Very simple. Here in TensorFlow, we used to define weight. That is something which we have to define. Then bias in TensorFlow, right? Then again weight 2, bias 2, and then forward propagation. You have to do calculation like that. Here it's very simple. For stochastic gradient descent also you have a package. You don't need to calculate the, you know, uh, partial derivatives. Don't need to calculate that with respect to all the layers out there. Simply you should pass loss equals to this and stochastic gradient. Then I think this is for TensorFlow. You don't need to worry about this. Nobody uses this. And once the model is created, you feed that on x and y values, x dot y values. Epochs is 10. What do you mean by epoch is equals to 10? Yes, guys. What is epoch is equals to 10? What do you mean by this, everyone? What is epoch is equals to 10, guys? What is your epoch is equals to 10, guys? Forward and backward propagation into 10 times. Correct, correct, correct. So for first epoch, you're getting this loss. Then loss is reducing. Can you see that? If you write on accuracy as well here, you'll get the accuracy. If you write on this, we'll see that. So since I have only written down loss, if you write on metrics is equals to accuracy, then I'll get that as well. So since we are writing down only loss, so we are getting loss. So for each after each epoch, we are reducing the loss. Then the model prediction is this for the first row out there. So I think you can try this. What I'll do is I already have given this to you on your drive, right? So everyone just build a model and then we'll see the next part. You guys have to build the model. This is your in-class activity now. Right? I have shared the file. It's not there. CSV, this file. You just download this file, guys, and start building the model. Do this. It's your first practice of building a deep learning model. So no one should only observe this. Everyone should build this. So do this, guys. Yes, guys. Are you guys doing this? Everyone? Let's do this. House price Keras. Right? Let's import the necessary libraries. So import pandas PD, import SNP, import sklearn, import TensorFlow, STF from TensorFlow, import Keras from sklearn dot preprocessing, import standard scalar from sklearn dot metrics, import accuracy score, right? Now, as part number one, we'll import the housing data and we'll do feature transformation. So LDF is equals to pd dot read underscore CSV. Let's copy this. So copy path, just over here, and df dot head, open and close bracket. Right? And if I write on x equals to df dot copy, open and close bracket, we'll remove target variable y is equals to x dot pop price, and we'll perform scalar transform of the input. Scalar is equals to standard scalar, and we'll fit transform that. Then we'll perform log transformation. Perform log transformation of target variable y is equals to np dot log of y. Then we'll do scaling. Df underscore scale is equals to pd dot data frame x df underscore scaled is this. Right, so we have scaled the data. We have scaled the data. And then y, this is your y. Then there will be, after this, let's do the part two. We'll create a model. Now this time we are going to use Keras, not we will not be using, you know, TensorFlow. So from TensorFlow, import Keras. Right? And we will be, dealing with creation of the your model. So your model is equals to Keras dot sequential. Everything is assigned sequentially. Then model dot add Keras dot layers dot input shape is equals to x dot shape square bracket -1 comma this model dot add here dot layers dot dense 2 comma activation is equals to sigmoid model dot add keras dot layers dot dense 1 comma activation is equals to linear and then model dot summary bracket. Right? So these are the parameters that you guys will be having. These are the parameters that we have. Just just a bit. ठीक है. Then actually we have not discussed few topics related to TensorFlow. Yes, yes, yes. That is something which is left. So let's discuss this and then we'll stop. I mean, we'll see that practical part. See, the objective of this segment, Introduction to TensorFlow, is we are going to understand the knowledge of which will help you to build your own neural network by using TensorFlow. So the TensorFlow primarily, we are using it primarily to understand what is happening behind the scenes, and you're expected to be comfortable with high-end level APIs. And after that, like this is something which we are going to learn. But before that, this is necessary to learn about the capabilities of TensorFlow as a machine learning library, which specializes in deep learning. We'll see that. Then to get an understanding of coding paradigm of TensorFlow to perform simple coding tasks. Then to understand fundamentals of TensorFlow, such as its data structure, tensors, and certain mathematical operations that can be performed using ML library. And TensorFlow is nothing but an open source platform for developing end-to-end machine learning solutions. TensorFlow platform contains several services such as TensorFlow.JavaScript, Lite, Extended, and which are used to develop applications for browser, mobile platforms, and large production environment respectively. The platform has all the tools needed to build a solution and deploy it on different platforms. One part of, you know, the complete TensorFlow environment is the TensorFlow machine learning library, which will be covered in this session. And it's a deep learning library developed by Google. TensorFlow is developed by Google. It is widely used in the industry for several different applications. Some of these applications are, include text, smart text like Gmail, Google Translate, and Google Lens. And as the this is comparison as the time progresses, or as the time progressed, uh, there were invention of graphical processing unit, then TPUs. पहले तो initially it was CPU, like we were building a model by using CPUs. Then there was a concept of GPU, graphical processing unit, which you can see in Colab. And now since the arrival of TensorFlow library, we have TensorFlow processing unit or tensor processing unit, that is TPU. So that is also something which is very recommended, or in order to increase the performance of your model, you can use this. So if you just see, can you see this? We have T4 GPU, we have CPU, we have GPU, and some of these are paid. So 100 GPU, this TPU, like you can purchase additional units, computational units by using this. Like you have some, $12 per month for Google Colab Pro, and you can always change the processing unit and to get the performance. So this is comparison. Yeah, so we have seen this, then we have seen tensors, correct? Now it's time to see Uh, we have seen how do you declare tensors, mathematical operations on tensor, linear algebra also we have seen, and code implementation we are going to see now. So on this, if you just see, mm, correct. ठीक है, ठीक है. Okay, let's go to this now. Let's see this. Now, since the model is built, this is your model summary. These are the parameters that you have in this model. We'll define a function. Ef random underscore init underscore params open close bracket, and this w1 is equals to ef dot variable ef dot random dot normal ef dot random dot uniform 2 cross 2. b1 is this ef dot variable, w2 is this, and b2 is this, right? And this function is going to return w1 comma b1 w2 comma b2, right? And then we are going to define forward prop, and then z1 is equals to t dot mathematical multiplication of x comma w1 plus b1, h1 is equals to this ef dot math dot sigmoid of z1, z2 is this ef dot mathematical multiplication of this, and b2 is this, and h2 is equals to z2, and you'll return h2 over there. Now you'll compile your model. Model compile. Optimizer is equals to, you can use any optimizer. I'm using stochastic gradient descent. Uh, loss is equals to MSE. Metrics I'll be using as accuracy. Let's go for this. Model is not defined, is it? Then what was that? Okay, okay. We need to restart this because we have changed the runtime, right? Restart session and run on. Because we have changed the runtime, guys. So restart should be there. No such directory, is it? Right? Once the model is compiled, we'll fit it. Simple. Once the model is compiled, once this is done, we are going to fit it. Model dot fit x comma y dot values comma epochs is equals to 10 comma batch underscore size is equals to 32. Then model dot predict x comma 0. right? So can you see this accuracy is this? Getting it, guys? Clear? Simple way to fit the model. Very easy way to fit the model. Accuracy used for classification. Yeah, correct. Because can you find accuracy in regression problem? No. So why we are using this? We used to find R2 score, right? That's why we are not getting the good output. Because accuracy is not a metrics to judge the performance of your regression model. Simple. Understanding it, guys? This one clear till now? Any doubts in this? Just go through this. I'll give you 5 minutes of time. Just go through this. All right, guys. So now we'll try to understand how do you find the total number of trainable, excuse me, total number of trainable parameters, right? So what we'll be doing is, just a minute. Try to understand, correct, this one. We will implement the neural network using Keras, using Keras, and we will see this concept of we'll first of all implement the neural network using Keras for classification task. Right, so this is done. You already have done this. We have done this. We have completed this. Now we'll be doing this for MNIST dataset. That is your classification task, right? So let me share this notebook with you. Let me just first of all download this and let me give this thing to you. Let me create new folder. Today is day 35. Day 35, 8th Feb 2025. And I'll be writing down, rename this as, you know, mm, what we can do. Yeah, MNIST data. A very famous data set, widely used, you know, um, to study the neural network models. That is something which we are going to now study. So I'll be giving this on your drive. Control X, V, installation. Correct. And these two files, I'm going to add it to this. 1, 2, 3. All right, all right. Now let me just take this out and let me just share my screen. ठीक है, ठीक है. So done. Yeah. All right. I'll be sharing my screen now and we'll be trying to build the neural network for application for your what we can say classification model. Right. Let's see classification model now. So let me create this and let me start working on this manually. We'll be importing necessary libraries, guys. We'll be importing necessary libraries. So I'll not be importing that. I will directly, you know, take this and I'll be pasting it over here. Instead of writing it down, it's better to, copy and paste. Now MNIST data. We need to import, this files. The two files that I have shared, which is there on your drive. Right? And let me load the data. So data is equals to read_CSV train data. So copy path, paste it over here. And x_test is equals to read_CSV. This one. Right? And then I'm going to write on data.head and close bracket. Right? Now I'm going to extract feature variables and target variables. So data underscore y is equals to, see, what is this thing, guys? MNIST data set. As I have told you, it's a handwritten recognition, right? Handwritten image recognition. So there will be, the size is I think 28 by 28. Yes, 28 by 28. So 784. And there is one target variable. Like these are the pixels. These are the pixel and this is label. Like this particular image is handwritten 1. This is 0. This is 1. Right? So your target variable is nothing but label, and in that values, right? And your, you know, independent variables are this one. Your independent variables are this one. So data dot drop label comma axis is equals to 1. Data underscore x dot head open close bracket head of 2. Now we'll visualize the data. Data visualization. This img is equals to data underscore x dot iloc of 2 dot values dot reshare 25 28 comma 28 plt dot imshow img comma cmap is equals to gray. Right? And then I'm going to take state of data underscore I x underscore train comma x underscore value y underscore train y underscore value is equals to train underscore test underscore split data underscore x comma data underscore y comma test underscore size equals to 0.1 comma random underscore state is equals to 42. And then we do model building. Model is equals to keras dot sequential open and close bracket, and we'll be building this model. So keras dot layers dot input Yes, yes, yes. I think there was power cut in my area. All right. So what we were discussing is, guys, we were, understanding the this part. So there are multiple ways in which you can fit the model. Keras.sequential, keras.layer.dense. Instead of this, I can write down this as well. Keras.layer.input shape is equals to 784, comma, this, comma, keras.layers.dense 128, comma, activation is equals to ef.nn.ReLU, comma, keras.layers.dense 128, comma, activation is equals to tf.nn.ReLU, comma, keras.layers.dense, then, comma, activation equal to tf.nn.softmax. Okay, I should use ReLU, and in the last layer we should use the softmax activation function. Correct. So last layer, there will be only 10, because this classification, how many classes do we have? We have 10 classes. You can see we have 10 classes over here, 0 to 9. So 0, 1, 2, 3, 4, 5, 6, 9 are 10 classes. So in classification model, we have to use softmax, and there will be 10 classes. So in the output, 10 neurons will be there. In the output, there will be 10 neurons. So that's why 10 shape is there. If this is done, then what we'll be doing is we'll compile this. Simple model dot compile. We are going to compile it by using optimizer is equals to Adam loss is equals to sparse categorical cross entropy, comma, comma, matrix is equals to accuracy, and I'll be writing down model dot summary of the bracket. Getting it, guys? Variables. Okay, it's not variables. Why we are writing down this model dot compile? So this is your compilation. Now can you see it? 128. So parameters are very huge. They are the parameters. Then it's time for model training. So model dot fit it on x underscore train, comma y underscore train, comma batch underscore size is equals to 64, comma epochs is equals to 5, comma validation underscore data is equals to x underscore val, y underscore val. Then you evaluate the model evaluation, model dot predict x underscore test dot argmax x is equals to 1. Simple, right? And then img is equals to x underscore test dot iloc of 1 dot values dot reshape 28, comma 28. plt dot im show img, comma cmap is equals to gray. And then I'm going to print the predicted label is model dot predict x underscore test not argmax. Correct. X is equals to 1 of 1. Correct. Can you see this? So I'm predicting this first, and it is 0 only. So the predicted label is 0. Likewise, you can predict. Now accuracy initially, since we are giving only 5 epochs, so we are able to achieve accuracy as, just a minute. Can you see this loss? Loss is 0.1039. If you just increase the epochs, then there will be increase in the accuracy. So for each epoch, there will be reduction in the loss. There will be reduction in the loss. So that's what we have for this model building part. Simple. Everything is same. You just need to remember how you can, give the model first of all. So in the first input, I have 784 uh, neurons. Then in hidden layer, I have 128 neurons. That is dependent on me. That is dependent upon, I can do it or I cannot do it. I mean, it depends upon me or user, how much, you wanted to give in the hidden layer. So one, sec two, three hidden layers will be there. 1, 2, 3, 128, 128, and 128. Right? This is 784. This is input layer, this is hidden layer, and this is output layer. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Because as we have 10 classes, so 10 output layer will be there. Simple. So you go through this, guys. Go through this and let me know if you have any questions. We'll stop here for the day. In the next session, we'll be continuing the next part. So anyone has any questions in this? Till now, whatever is being discussed, anyone has any questions? Yes, guys. Any questions do you have? Any questions, any doubts? Yes, guys, do you have any questions, any doubts? All clear? Why 10 classes for the output layer? Yes. Is it classification or regression, guys? Yes, Murli. That problem is classification or regression. It was for classification. So how many output do you have? How many how many classes do you have? You have to predict whether this image belongs to 0 class or 1 class or 2 or 3, 4, 5, 6, 7, 8, 9. How many classes are there then? Multi-class classification, no? 10 classes. So it has 10 classes, so 10 output neurons, right? Whether that particular data belongs to 0 or 1 or 2 or 3 or 4 or 5, 6, 7, 8, 9. These are the classes. You have to identify that. Simple. Understanding it, guys? All right, then, guys, we'll stop here. Thank you, everyone. Happy learning. Bye.